Sedna should not be where it is. That is not a dramatic way of framing something complicated. It is the literal result of running the numbers. When Mike Brown and his team picked it up in 2003, they did the orbital calculations and found a perihelion, the closest point of its orbit to the Sun, sitting at 76 astronomical units out. Neptune is at 30. The broad disk of icy rubble beyond Neptune, the Kuiper belt, thins out around 50. Sedna never comes closer than 76. It reaches its farthest point at roughly 937 astronomical units from the Sun, a distance so extreme that light itself takes more than 5 days to travel it. One complete trip around the Sun takes 11,400 years. And there is nothing in the standard account of how this solar system assembled itself that puts an object out there. Not outside the expected range by a small margin. Not anomalous in a way that requires a modest adjustment. Outside the model entirely, in a region the model does not even reach. Brown said at the time that Sedna was the most distant object ever found in the solar system, and that its orbit made no sense. That was not rhetoric. That was a precise description of what the physics could and could not account for. What you do with something that makes no sense depends entirely on your situation. Most of the time in science, an anomalous object gets filed. It sits in a catalog alongside mundane things, accumulating a designation and a set of orbital parameters, waiting. It gathers dust in databases. Only when there are enough objects like it does someone begin to ask the real question, not just whether the model is wrong, but whether the model is wrong in the way that requires replacing it entirely, or wrong in the way that requires something to be added to it. That distinction matters more than it might initially appear. A model that is fundamentally wrong has to be torn down. A model that is mostly correct but missing one piece can be preserved almost intact. The second option is almost always preferred, because it is tidier, because it preserves more of what everyone already believed, and because the history of science is populated by people who found it easier to add an epicycle than to abandon the system that required it. By 2014, Sedna had a companion, an object designated 2012 VP-113, informally called Biden by the astronomers who found it, for the initials VP had a perihelion of 80 astronomical units. Chad Trujillo and Scott Shepard announced it in March of that year, and in the same paper they noted something that had been completely invisible when Sedna was the only object of its kind. The two bodies shared a striking similarity in a specific orbital parameter called the argument of perihelion. This is the angle that describes the orientation of an orbit in space, roughly speaking, which direction the long axis of the ellipse points relative to the plane of the solar system. For Sedna and 2012 VP-113, these angles were close, not identical, but close in a way that felt like it was trying to communicate something rather than saying nothing at all. Trujillo and Shepard looked at a wider population. They found 12 extreme Trans-Neptunian objects, the formal name for bodies in highly elongated orbits far out beyond Neptune, all showing a similar concentration in this orbital angle. They proposed that an undiscovered massive planet somewhere between 200 and 300 astronomical units from the Sun was perturbing these objects, holding their orbits in alignment through a mechanism called the Kozai effect, which describes how a sufficiently distant massive body can lock certain orbital parameters of smaller objects into configurations that remain stable across enormous spans of time. This was not the first time anyone had proposed a large outer planet. The history of that proposal is longer and stranger than most accounts bother to acknowledge, and it matters here not as background noise, but because the shape of that history is itself a kind of evidence, not evidence about the solar system, but evidence about how human beings have historically reasoned about it. and what has happened every time they were certain they had found a mathematical planet before they found a physical one. George Forbes, a Scottish engineer and astronomer, proposed 2 Trans-Neptunian planets in 1880, based on what he believed he could see as a clustering in the aphelion distances of long-period comets. The proposal went nowhere, but the logic was structurally identical to what would come more than a century later. Things out there are behaving in a way that suggests something large is hurting them. In 1902, Percival Lowell began his search for what he called Planet X, using irregularities he believed he could detect in the orbits of Uranus and Neptune as his primary evidence. He searched from his observatory in Flagstaff, Arizona, until his death in 1916, and never found it. The search continued under his name and his institution's funding after he was gone. In 1930, a 23-year-old farm boy from Kansas named Clyde Tombaugh, who had been hired to perform the tedious photographic plate work that no senior astronomer wanted to do, found a small moving object in the constellation Gemini. It was near where Lowell had predicted his planet would be. They called it Pluto. The problem was visible immediately to anyone willing to look carefully at the numbers. Pluto was far too small to be the planet Lowell had been calculating toward. Lowell had determined that Planet X needed to be roughly 7 times the mass of Earth to produce the perturbations he believed he was seeing in the orbits of Uranus and Neptune. Pluto, it became progressively clearer over the decades that followed, was nowhere near that. In 1978, when James Christie discovered Pluto's moon, Charon, it became possible for the first time to calculate Pluto's mass with real precision. It came out at 0.2% of Earth's mass, less than 1/400th of what Lowell's model had required. But the perturbations Lowell had measured were real. He had not imagined them. They turned out to be something entirely different from what he had thought, an artifact of imprecise measurements of Neptune's own mass. When Voyager 2 flew past Neptune in 1989 and returned an accurate mass figure, those perturbations dissolved completely. The irregularities that had sent Lowell on a search lasting over a decade, that had consumed an observatory's resources across generations, that had ultimately produced Pluto as a kind of accidental byproduct of the wrong hypothesis, were not perturbations at all. They were errors in the measurement of the thing supposedly being perturbed. Pluto is real. It is out there right now, roughly 50 astronomical units away, taking 248 years to complete one circuit of the Sun. But it is not Lowell's planet. It was not found because the mathematics worked. It was found because a young man from Kansas was willing to stare at photographic plates 8 hours a day in a cold building, and because the portion of sky near his comparison region happened to contain a small icy world that moved visibly between exposures. It was found because of the search, not because of the prediction. The prediction was wrong in almost every particular. The method that generated the prediction was wrong at its foundation, and the lesson the astronomical community drew from the discovery was complicated. Because something had been found in roughly the right place by the predicted method. So the method acquired a form of credit it may not have fully deserved, and that credit would compound over the decades that followed. Konstantin Batygin was candid about this history when asked about it in later years. He and Mike Brown had spent years dismissing Planet X proposals as wishful thinking, as exactly the kind of pattern-seeking that the outer solar system seemed to invite whenever someone stared at it long enough. Brown had made part of his professional reputation by removing planets from the solar system. His work on Kuiper belt populations was central to the argument that led to Pluto's reclassification as a dwarf planet in 2006. He was not a man inclined to add planets. When he began to think that something might genuinely be out there, he did not say so immediately. Neither did Batygin. By their own account, They first spent considerable time trying to explain the clustering away. They looked for alternative mechanisms. They ran the numbers against the null hypothesis, the possibility that the alignment was simply chance, and found a probability they could not responsibly dismiss. That probability was 0.007%. That figure entered public consciousness in January 2016, when the paper appeared in the Astronomical Journal. 0.007% chance that the clustering of 6 extreme trans-Neptunian objects was the result of random alignment. Odds of roughly 14,000 to 1 against it being coincidence. 6 objects were behaving in a way that should have been essentially impossible without something very large and gravitationally powerful somewhere nearby. And no one had ever detected that something directly. The phrase that attached itself to the finding almost immediately was mathematically certain. Not in the paper itself, Battigan and Brown were careful with their language, but in the coverage, in the conversations, in the way the finding propagated through public discourse. The math says it is there. The planet exists. We simply have not found it yet. The certainty was in the calculation, and the calculation was built on the data, and the data came from 6 real objects with real orbits that real telescopes had tracked across real years. This is where something needs to be pressed on carefully, because the phrase mathematically certain is doing a specific kind of work in this context that deserves genuine examination before being accepted. Mathematical certainty is a precise term with a precise meaning. It refers to statements that can be proven to follow necessarily from axioms within a formal system. The calculation that Battigan and Brown performed was not that kind of certainty. It was a statistical inference. Given the observed data and a model of how orbits should be distributed in the absence of a perturbing planet, the probability of seeing this degree of clustering by chance is very small. That is meaningful. It is important. It is not the same thing as certainty, and treating it as though it were obscures the specific nature of what the finding actually established. The difference matters because statistical inference is always conditional on the sample being representative of the population it is drawn from. If those 6 objects were drawn from a genuinely random sample of the outer solar system, the inference is strong, and the low probability figure is telling you something real about the solar system. If the sample was not random, if the way those 6 objects came to be known is itself biased in some systematic direction, then the probability calculation is not wrong in its arithmetic. It is wrong in what it is measuring. It would not be measuring the probability that the outer solar system is intrinsically clustered. It would be measuring the probability that a biased sample of the outer solar system looks clustered, which is a fundamentally different calculation producing a fundamentally different answer. Battigan and Brown knew this. They addressed it briefly in the 2016 paper. They noted that the 6 objects had been discovered by 6 different surveys operating at 6 different telescopes, and argued that this independent discovery pattern made a systematic bias considerably less likely. The argument is reasonable. It is also not conclusive. And the reason it is not conclusive only becomes visible when you think carefully about the specific nature of the bias being proposed, rather than the simpler version of bias that the 6 survey argument effectively answers. The bias is not about any single telescope. It is not about any single survey team making a directional choice. It is about the structure of ground-based astronomical observation itself, at a deeper level, which parts of the sky can be effectively searched from the ground, at what times of year, during what weather conditions, near what galactic latitudes, to what depths of sensitivity. A telescope in Hawaii and a telescope in Chile and a telescope in Arizona are not 3 genuinely independent perspectives on the outer solar system. They are 3 instruments operated from the same planet, under the same sky, rotating through the same seasons, constrained by the same galactic plane that fills certain portions of the sky with so many background stars that finding faint moving objects against them becomes extremely difficult, following up the same objects that appear interesting by criteria that every survey in the field shares. Their specific biases differ from one another in detail. Their structural biases share a common root. Before pressing any further on that structural bias, it is worth stopping completely and sitting with what Planet 9 would actually be if it exists. Not the orbital mechanics, not the statistical argument, the physical thing itself. Somewhere between 500 and 700 astronomical units from the Sun, the best current estimate, revised considerably downward from the 800 astronomical units of the original 2016 paper, there is an object roughly 4 to 5 times the mass of Earth. At that distance, light from the Sun takes between 69 and 97 hours to make the journey. The Sun, seen from there, would be a point of light, still the brightest thing in the sky, bright enough to cast faint shadows, but small enough to fit behind your thumbnail at arm's length, delivering no warmth whatsoever. The object would be cold, perhaps 47 Kelvin above absolute zero, which is 226 degrees below the freezing point of water. It would be dark. It would reflect almost nothing. Its orbital period is somewhere between 10,000 and 20,000 years. That means that in the entire span of recorded human history, from the first cuneiform astronomical tablets pressed into clay in Babylon, to the medieval Islamic astronomers who mapped the sky with unprecedented precision, to Galileo, to Newton, to the Hubble Space Telescope, to this present moment, this object has moved roughly 1/60th of the way around its orbit. The civilizations of ancient Greece rose and fell and were partially forgotten before it completed even a fraction of a single lap. And in all that time, with all the instruments and all the eyes and all the accumulated weight of human curiosity directed at the sky, we have not detected it once. That is not on its face surprising. The outer solar system is genuinely immense, and the search area is correspondingly vast. But it is worth holding clearly in mind. We are being asked to believe in something that has been present throughout the entire history of human astronomy, that has passed through the same regions of sky our instruments have catalogued across centuries, that has left no direct mark on any observation ever made. Everything we have is the behavior of other things, things that are too far from the Sun, or tilted too strangely, or oriented in directions that the models say they should not occupy. The thing we are inferring is known only by what it does to its neighbors, and its neighbors are very few in number and very difficult to find. In 1846, Urbain Le Verrier sat in Paris with a pencil and a considerable stack of calculations and predicted the location of a planet no one had ever seen. He sent the coordinates to Johann Galle at the Berlin Observatory. Galle turned the telescope to the designated point in the sky. Within 1 degree of the predicted position, there it was, a faint disk with a greenish tint that was not on the star chart he was using. That story is the foundation on which all subsequent mathematical planet predictions rest. The entire intellectual lineage that eventually produced the Planet 9 hypothesis flows from that single night in Berlin, and the story is not quite what it appears to be. Le Verrier's prediction was wrong. Not wrong in the sense that Neptune did not exist. Neptune was there, right where Galle pointed, solid and real and waiting to be named. Wrong in the numbers, wrong in the underlying model, wrong in almost every physical parameter that Le Verrier had calculated, in ways that should, strictly speaking, have meant the telescope was pointing at empty sky. Here is what Le Verrier actually predicted: a planet orbiting at roughly 36 astronomical units from the Sun, with a mass approximately twice Neptune's actual mass, tracing an orbit with an eccentricity, a measure of how elongated an ellipse is, significantly higher than Neptune's real orbit. Neptune actually sits at 30 astronomical units. Its mass is just over 17 times Earth's. Leverrier's predicted mass was roughly double that. His predicted orbital distance was off by 20%. The shape of the orbit he described was wrong. The planet he had calculated on paper was not the planet that Gall found through the eyepiece. And yet, the telescope found it, within 1 degree of the predicted position, on the first night of looking. The question that has occupied historians of science ever since is the obvious one. How does a calculation that is wrong in its fundamental parameters produce a prediction that is right in its positional result? The answer is genuinely not simple, and it is not the answer that the triumphant story of Neptune's discovery is usually held to demonstrate. Both Leverrier and John Couch Adams, the English mathematician who independently made a similar prediction, setting off the bitter priority dispute that consumed the scientific establishment for years afterward, had anchored their calculations to something called Bode's law, sometimes called the Titius-Bode's law. This is an empirical numerical relationship between the distances of the known planets from the Sun. It is not derived from any physical principle. It is not a law in any physical sense at all. It is a pattern, a numerical coincidence that holds approximately for the inner planets, and that was assumed in the early 19th century, in the absence of any reason to doubt it, to hold for outer ones as well. The law predicted a planet at approximately 38.8 astronomical units from the Sun. Neptune is at 30. The Bode's law distance is wrong by about 23%. So both predictions began not with correct physics, but with a wrong numerical assumption about where the planet would be. They then each calculated what mass and orbital shape would be necessary to produce the observed perturbations in Uranus from that wrong assumed distance. A planet at 38 astronomical units would need to be more massive and orbit on a more elongated path to produce the same gravitational effect as a planet at 30 astronomical units. The mathematics was internally self-consistent. It was also self-consistently built on a false premise. What saved the prediction from pointing at empty sky was a specific coincidence of orbital geometry. In 1846, Neptune happened to be near the particular point in its orbit where the difference between its actual position and Leverrier's predicted position was at its smallest. The two orbits, the real one and the calculated one, intersected near each other at precisely that moment in planetary time. An astronomer searching in 1846 for the object at Leverrier's predicted location would find Neptune nearby, within the field of view of an instrument of that era. Had the same search been conducted 10 years earlier, or 15 years later, Neptune would have been elsewhere along its orbit. The real and the predicted positions would have diverged significantly, and Leverrier's coordinates would have pointed at an unremarkable field of stars. This is documented. It is not a fringe reading of the evidence. Historians who examined the original calculations in detail established that the positional agreement between prediction and discovery was a product of a specific orbital coincidence, not of the accuracy of the underlying model. Neptune's orbit is nearly circular, which means it has a roughly equal probability of being near any given point in its path at any given time in history. In the early 1840s, it was moving toward the position where Leverrier's wrong prediction would happen to intersect its actual path. By the mid-1850s, it would have moved past that intersection point. The window was narrow. Leverrier worked within it without knowing it existed. This is not meant to diminish what he accomplished. The mathematics of celestial mechanics he performed, accounting for the gravitational perturbations of multiple planets simultaneously on a single body. then reversing the entire problem to infer the nature of the perturbing body from the observed perturbations, was operating at the absolute frontier of what was computationally possible in the 1840s, without any device more sophisticated than a table of logarithms and a patient mind. Leverrier spent years on the problem. He developed new mathematical tools to solve it. His native ability was genuine, formidable, and widely recognized. The later character who emerges from the historical record, the man who tried to name Neptune after himself, who became the most feared and autocratic observatory director in the history of French astronomy, who was eventually removed after his senior staff collectively and formally demanded his dismissal, who was then reinstated 6 years later when his successor proved less capable, who died in the director's chair in 1877, that man's mathematical talent was not in question. What is in question is what his specific success with Neptune actually demonstrated about the method he used. The success was reported everywhere as a triumph of Newtonian mechanics. Theory predicted a planet, observation confirmed it. This is how it entered the textbooks, how it was transmitted to subsequent generations, how it became the founding narrative of mathematical planet prediction. The philosopher William Whewell coined the term consilience of inductions partly in response to it. The idea that when independent lines of reasoning converge on the same conclusion from different directions, that conclusion is powerfully supported. Neptune appeared to validate this principle in the most spectacular and public manner imaginable. A man with a pencil pointed at a specific location in the sky and said, "There." And there it was. What was not reported with equal prominence was that the numbers were wrong, that the distance was off by 20%, that the mass was wrong by a factor of 2, that the orbital shape was incorrect, that the planet found in the eyepiece was not, in any precise physical sense, the planet that had been calculated on paper. The prediction had the right general region of sky at the right historical moment, for reasons that were partly physically correct and partly a matter of fortunate timing, and the instruments of the era lacked the precision to reveal the discrepancy between calculation and reality. By the time more accurate observations established Neptune's true orbital parameters, the triumph had already been written irreversibly into the history of science, and the inaccuracies had retreated quietly into specialist footnotes that most people who told the story never encountered. Leverrier went further. Emboldened by Neptune, by the cultural narrative of Neptune, which was perhaps even more intoxicating than the planet itself, he turned to Mercury. Mercury's orbit had a known anomaly that had been accumulating in the observational record for some time. Its perihelion was precessing, slowly advancing around the Sun at a rate slightly greater than Newtonian mechanics could explain, even when all the known planets were included in the calculation. The discrepancy was small by any everyday measure, 43 arc-seconds per century, which is an angle so tiny you could not see it directly. But it was real, and it was persistent, and Leverrier measured it with the precision his methods allowed. He then calculated that an undiscovered planet orbiting inside Mercury's orbit, close to the Sun, could account for this residual precession. He named that planet Vulcan. He announced its existence in 1859, the same year Darwin published On the Origin of Species. And he held the conviction about it with the same unshakable certainty he had brought to Neptune. The structural analogy between Vulcan and Planet 9 is not a casual comparison made for rhetorical effect. It is precise. Unexplained residuals in observed orbits. A mathematical inference of a massive unseen object. A prediction of that object's location and characteristics expressed with numerical precision. A public announcement made with confidence. Then search. Vulcan was searched for with genuine seriousness and considerable effort. During total solar eclipses, when a planet close enough to the Sun might become briefly visible in the darkened sky, teams of professional astronomers positioned themselves along the path of totality and scanned the corona. Between eclipses, amateur and professional observers sent reports of apparent sightings, small round disks crossing the face of the sun in what appeared to be transit. Leverrier himself found some of these reports credible enough to endorse. A country doctor named Edmond Lescarbot claimed to have observed Vulcan transiting the sun in 1859 and wrote a letter to Leverrier, who traveled to visit him in person, inspected his notes and instruments, came away satisfied, and formally presented him to the Académie des Sciences as the discoverer of the new planet. He arranged for Lescarbot to be awarded the Legion of Honor. Vulcan did not exist. The residual in Mercury's orbit was real. Leverrier had measured it correctly, within the precision his instruments permitted. But the explanation was not a planet inside Mercury's path. The explanation was that Newtonian mechanics was not quite right, that at the scale of Mercury's proximity to the Sun's enormous gravitational mass, space and time behaved slightly differently from what Newton's equations predicted. The true explanation arrived in November 1915, when Einstein published the field equations of general relativity. When he applied his new framework to Mercury's orbit, the 43 arc-seconds per century fell out of the mathematics exactly, without any additional planet being required, without any free parameter to adjust, without any fudging. Einstein later wrote that when he saw the number emerge correctly from his equations, he had palpitations of the heart. He was unable to work productively for several days. What Leverrier had found was not Vulcan. He had found the first empirical evidence that Newtonian gravity was incomplete. He had found a real signal pointing not outward toward an undiscovered planet, but inward toward a gap in the most successful physical theory the world had yet produced. The signal was absolutely real. The inference from it was completely wrong. And the inference was wrong not because Leverrier was careless or credulous or insufficiently skilled, but because within the conceptual framework available to him, a gravitationally perturbing planet was the only available explanation. The framework itself was the thing that was wrong. And frameworks, from the inside, are invisible as frameworks. They look like reality. The question this puts to Planet 9 is genuinely uncomfortable, and it needs to be asked directly rather than skirted. Is the anomaly in the outer solar system a signal pointing outward, toward an undiscovered planet waiting to be found? Or is it a signal pointing inward, toward something we do not yet fully understand about how the outer solar system formed and why it behaves the way it does? The two possibilities are not equally exotic in the sense of requiring extraordinary new physics. One requires a planet, which is conceptually familiar. The other requires a recognition that our models of outer solar system formation are incomplete in ways we have not yet fully characterized, which is less dramatic, but perhaps no less significant. Samantha Lawler, an astronomer at the University of Regina in Canada, who has spent years studying Trans-Neptunian object populations, has argued in detail that Neptune's own migration, the process by which Neptune moved outward from its original orbital position during the early solar system's dynamical evolution, can account for many of the orbital peculiarities that the Planet 9 hypothesis was constructed to explain. The nice model of solar system formation, named for the city in France where it was developed, proposes that the giant planets originally formed in a more compact configuration and migrated outward over the first few 100 million years, driven by gravitational interactions with the surrounding disk of smaller bodies. Neptune, in this model, moved outward substantially, crossing orbital resonances, scattering smaller objects across enormous distances, reshaping the entire architecture of the Kuiper belt as it went. The highly eccentric and steeply inclined orbits that characterize the outer solar system's extreme population may be the frozen record of that migration, objects scattered and deposited in their current paths by a Neptune that no longer occupies the position it once held. Lawler's detailed computer simulations showed that all but the two highest perihelion extreme Trans-Neptunian objects could be explained by known physical effects without invoking Planet 9 at all. The outer solar system may be strange not because something large is herding it from the outer dark, but because the process that assembled it was itself violent and complex, and we are only beginning to reconstruct the details of that ancient chaos. This is the interpretive fork that the Neptune triumph effectively closed off for subsequent generations. When Neptune was found where Leverrier pointed on that September night in 1846, it communicated something to everyone who came after. The method works. Unexplained gravitational residuals mean planets. Mathematics can find what the eye cannot see. The appropriate response to an anomaly is to calculate the object causing it and then point the telescope. The method was canonized by its success, and the portion of that success that depended on a coincidence of orbital geometry that could have gone the other way, the portion that was luck, was dissolved into the triumph narrative and effectively forgotten by everyone who transmitted that narrative to the next generation. What was transmitted was not a method with a known success rate and known failure conditions. What was transmitted was a template. Strange behavior in known objects implies a perturbing body. Calculate the body. Search for it. This template has been applied repeatedly across the history of astronomy. Forbes applied it to long-period comets in 1880 and found nothing. Lowell applied it to the orbital irregularities of Uranus and Neptune from 1902 until his death and found nothing, though his search accidentally produced Pluto. A physicist named Joseph Brady applied it to residuals in the orbital timing of Halley's Comet in 1972 and predicted a massive planet 3 times the mass of Saturn in a retrograde orbit at 59 astronomical units. Brady's planet was searched for and never found because it does not exist, and because the residuals in Halley's timing that he was trying to explain were measurement artifacts rather than genuine gravitational signals. Trujillo and Shepard applied it to the clustering of Sedna and its apparent companions in 2014. Batygin and Brown applied it to 6 extreme Trans-Neptunian objects in 2016. The template has produced one confirmed detection, Neptune, out of at least 5 serious applications over more than a century. 1 is not 0. Neptune is real, and the method found it. But a template that has worked once and failed on the 4 other occasions it was seriously applied is not a template that warrants the cultural confidence that phrases like mathematically certain carry. It is a template that warrants careful use alongside careful skepticism. It is a template that needs its assumptions examined fresh each time it is applied, not deferred to on the authority of a single famous success from 1846 whose details turn out under scrutiny to be more complicated than the story transmitted about them. There is one more element of the Neptune story that has not yet been fully pressed, because it connects directly to the nature of the evidence Batygin and Brown were working with in 2016. Leverrier's evidence, the anomalous precession in Uranus's orbit, was drawn from a single planet, tracked continuously across many decades by multiple independent observers using progressively improved instruments. The dataset was coherent, deep, and well understood in terms of its measurement uncertainties. When Leverrier found a residual in that data after accounting for the gravitational influence of all known planets, he had strong grounds for confidence that the residual was physically real, that it was something happening in the solar system and not an artifact of his instruments or his methods. The clustering that Batygin and Brown found was in a sample of 6 objects gathered across roughly a decade by different teams, with different instruments operating at different sensitivity levels and different observational cadences. Each object had been found once, tracked for long enough to establish an approximate orbit, and then largely left to its own devices in the catalogue. Leverrier had decades of continuous precise planetary data. Batygin and Brown had 6 objects and 6 orbital solutions. 6 is a genuinely small number, when you are using it to calculate probabilities about the architecture of the solar system. The Canada-France-Hawaii telescope sits near the summit of Mauna Kea at an elevation of 4,204 meters. The air at that altitude is dry and thin and remarkably stable, in a way that almost no other site on Earth can consistently match. On a good night, the seeing, the technical term for the degree of atmospheric turbulence that limits how sharply a telescope can resolve distant objects, is among the finest available anywhere on the planet. The mirror is 3.6 meters across, which is not large by contemporary standards. But for the specific work of surveying large patches of sky to faint limiting magnitudes, of finding objects that move slowly and faintly against an enormous background of distant stars, and of tracking those objects across months and years long enough to pin down their orbits, it is one of the most capable instruments that has ever been directed at the outer solar system. From 2013 to 2017, a collaboration of 40 astronomers from 8 countries used it to conduct a survey called OSOS, the Outer Solar System Origins Survey. The lead investigators included Michelle Bannister, Brett Gladman, Jean-Marc Petit, and a doctoral student at the University of Victoria named Corey Shankman. They chose 8 specific patches of sky, returned to each patch repeatedly across 4 years of observing, and built a systematic picture of everything that moved against the fixed stars. They found 840 Trans-Neptunian objects. That was approximately double the number with well-characterized orbits that had existed before the survey began. But the sheer number of objects discovered was not what distinguished OSOS from every survey that had come before it. What distinguished it was something they built alongside the catalog, a complete, systematically quantified record of their own observational biases. Every astronomical survey has biases, and this is not a criticism of any specific survey. It is simply a description of what a survey is.
A survey is a series of choices: where to point the telescope, on which nights, for how long, to what limiting magnitude, with what follow-up criteria for confirming candidate detections. Every one of those choices admits certain objects into the catalogue and excludes others. A survey that points primarily along the ecliptic plane, the great circle on the sky traced by the sun over the course of a year, finds more solar system objects than one that avoids it, because most solar system bodies orbit near the plane of the planets.
A survey conducted predominantly in autumn finds objects in a different portion of the sky than one conducted predominantly in spring, because the Earth's position around the sun determines which parts of the outer solar system are accessible at any given time of year. A survey that uses a relatively bright limiting magnitude detects only the largest and closest objects in a given population, systematically missing the smaller and fainter majority. None of these effects constitute errors or failures of scientific practice. They are the inevitable consequences of operating finite instruments under real physical constraints. But they mean that what you find is shaped in non-trivial ways by how and where and when you look. What OSOS did, with a degree of systematic rigor that had not previously been attempted in surveys of the outer solar system, was to characterize every one of these selection effects for every one of their 8 survey blocks individually. For each object detected in the survey, they calculated the probability that an object of that specific brightness, at that specific position in the sky, on that specific type of orbit, would have been detected given all the actual observational conditions that were in place when the survey was operating in that region of sky. This tool, the survey simulator, is the instrument that allows you to step from what your survey found to what is actually out there in the solar system. It is the mechanism for correcting the inevitable distortions that arise when you can only look from one place, in one direction at a time, for finite amounts of time, under the constraints of a rotating Earth and a sky that is partially obscured by the galaxy itself. The result of 4 years of work was not simply a catalogue of 840 trans-Neptunian objects. It was a catalogue of 840 objects, each tagged with a precisely calculated detection probability, embedded within a fully characterized model of what the survey could and could not have found under its specific conditions. It was, in the language of the field, a bias-characterized survey, and it was at the time of its completion the most carefully characterized survey of the outer solar system that had ever been executed. When Shankman and his colleagues examined the extreme trans-Neptunian objects in their sample, specifically those with semi-major axes large enough and perihelia distant enough to be dynamically relevant to the Planet 9 hypothesis, they found 8 objects. Among those 8, they looked for the clustering that Batygin and Brown had identified in the original 6, the concentration of longitudes of perihelion, the tendency for the long axes of the most distant orbits to align in a common direction. When they applied their survey simulator, when they corrected for the specific biases of their own observations, and asked what the underlying population would need to look like to produce what they actually detected, the apparent clustering dissolved. The distribution of the 8 objects was consistent with uniformity. Their orbits pointed in no strongly preferred direction. Their conclusion, stated with deliberate precision, was this: they found no evidence for the orbital clustering that the Planet 9 hypothesis required in their fully independent, bias-characterized sample. That sentence carries a weight that is easy to slide past. Not, we found evidence against the existence of Planet 9. Not, we demonstrated that no planet is present. Specifically, we found no evidence for the clustering, in a survey built expressly to be capable of detecting that clustering if it existed. With a sample that, once corrected for all the observational biases the team could characterize, showed a distribution consistent with randomness. Batygin and Brown did not accept this as settling the question, and their reasons were not mere defensiveness. They were substantive scientific objections. Their central argument was this: Assos found 8 relevant objects. Of those 8, the distribution was not a clean refutation. Some pointed in roughly the expected direction, some opposite, which is actually partially consistent with the Planet 9 model, since that model predicts both a clustered population and an anti-aligned population. Most critically, 8 objects is a very small number from which to draw a definitive statistical conclusion. 4 relevant objects cannot reliably distinguish a genuine underlying signal from the noise of small number statistics. Assos had built the most careful bias model in the field's history, Brown argued, and it was still too small a sample to constitute a meaningful test of the clustering. Both things are simultaneously true, and that is precisely why the debate has persisted. Assos found no clustering in a bias-characterized sample. That is the kind of evidence that should be taken seriously. Assos found only 8 relevant objects. That limits its statistical power to detect a real signal that might genuinely be present. The survey was the most careful ever done. It was also not large enough to be decisive. But there is something in the architecture of this disagreement that needs to be examined before it is accepted as simply an empirical dispute waiting for more data. The two sides are not disagreeing about numbers. They are disagreeing about what constitutes evidence in the first place, and specifically about which kinds of evidence deserve more weight. Batygin and Brown's original argument rested on the observed clustering in a sample that had not been characterized for observational bias. Assos characterized its sample for bias and found the clustering absent. Batygin and Brown responded by arguing that the original sample was nevertheless trustworthy despite the absence of formal bias characterization, because it had been assembled from 6 independent surveys. This is their strongest single argument, and it needs to be engaged with honestly rather than dismissed. Here is the honest engagement. The 6 surveys that contributed objects to the original Batygin and Brown sample were not selected at random from the set of all possible outer solar system surveys. They were selected from the set of surveys that happened to successfully find extreme trans-Neptunian objects. That is a considerably smaller and potentially more systematically skewed set. Surveys that find extreme trans-Neptunian objects are surveys that looked in the right places, at the right times, with the right instrument sensitivity, and deployed the right follow-up resources. They share, not identically, but structurally, the characteristic of having been capable of detecting objects in certain orbital configurations rather than others. The surveys that did not find extreme trans-Neptunian objects did not contribute objects to the sample, but their non-detections are also scientifically meaningful data. They tell you something about where these objects are not, which constrains your knowledge of where they are. By drawing a sample only from successful surveys, you are conditioning on a specific kind of outcome in a way that is subtle but not harmless. This conditioning effect, selecting only the surveys that found things, can introduce a shared directional preference even across multiple apparently independent programs. Because all the programs that found things are programs that were capable of finding things, and the conditions under which trans-Neptunian objects are detectable from the ground are not uniformly distributed across the sky. This is the point at which the six-survey argument, while valid as a defense against the simplest form of the bias objection, begins to show its limits. Kevin Napier and his colleagues at the University of Michigan made the empirical test more rigorous in 2021. They assembled 14 extreme trans-Neptunian objects drawn from 3 independent surveys, 5 from OSOS, 5 from the Dark Energy Survey, and 4 from a third independent program, and asked whether their combined orbital distribution showed the clustering that would be expected if Planet 9 were present. Each of the 3 surveys had characterized its own observational biases. The result was unambiguous in its direction: no statistically significant clustering. The joint probability that the observed distribution could arise from chance in a uniformly distributed underlying population was not 0.007%. It was high, somewhere between 17 and 94%, depending on the specific assumptions made, depending on which objects were included, and how stability criteria were applied. The clustering was not there. Napier put it plainly, "It really looks like we just find things where we look," he said. The surveys were like people who lost their keys at night and searched under street lamps, not because they believed the keys were there, but because that was where the light was. 3 independent bias-characterized surveys finding no clustering is a qualitatively different kind of result from one survey finding no clustering. It begins to establish a pattern. Every time the observational correction is carefully applied, the signal diminishes. The clustering is present in uncorrected samples and absent in corrected ones. That asymmetry is not proof of anything by itself, but it points in a consistent direction. Samantha Lawler's simulations at the University of Regina made this explicit in a way that the statistical arguments alone could not. She and her colleagues modeled what extreme trans-Neptunian object discoveries would look like if the underlying population were completely uniform, no Planet 9, no intrinsic alignment, just objects distributed randomly in all orbital orientations, but observed only through the actual survey strategies and sky coverage of the programs that had contributed to the existing catalog. The result was striking. The simulations showed that in a genuinely uniform underlying population, the apparent clustering of discovered objects would concentrate naturally in specific ranges of longitude of perihelion, the ranges where surveys were most likely to detect objects, given seasonal constraints, galactic plane avoidance, follow-up feasibility, and the geometry of perihelion detectability, were not uniformly distributed around the sky. They were concentrated in certain directions. Those directions overlapped substantially with the clustering that Battigan and Brown had found in the original 6-object sample. The implication was direct. The null hypothesis, no planet, uniform underlying population, predicts an apparent clustering that looks qualitatively similar to what was observed. The 0.007% probability was calculated against a perfectly uniform expectation. Against an expectation that accounts for the actual survey geometry and detection conditions, the probability is higher. How much higher is precisely what is uncertain, but the simulation established clearly that the simple comparison against a uniform distribution was not the right comparison to make. There is a technical point that Battigan and Brown have correctly pressed back on in response to this argument, and it should be given its due weight. The clustering they reported was not in a single orbital parameter. It was simultaneous clustering in 2 independent parameters, the longitude of perihelion and the orientation of the orbital plane itself, a spatial clustering in addition to the angular one. 2 parameters clustering together is a more demanding signal than 1 parameter alone. Lawler's simulations demonstrated that survey geometry can produce apparent clustering in longitude of perihelion. They did not establish with equal clarity that survey geometry can simultaneously produce clustering in the orbital plane orientation to the same degree. The 2-parameter clustering is the stronger version of the signal, and it is the version that has been less completely addressed by the bias argument. This is where the honest accounting of the uncertainty lands. The single-parameter clustering, longitude of perihelion considered alone, is substantially weakened by the bias argument and by the Osso's and Napier results. The 2-parameter clustering, the simultaneous alignment in both orbital angle and orbital plane, is less thoroughly accounted for and represents the most difficult remaining challenge to the bias explanation. Not proof of a planet, not even close to proof, but a harder thing to dismiss with the bias argument alone. Now there is a layer of bias that needs to be named that neither side of this debate has fully addressed, because it lives not in the instruments but in the human pipeline between a detection and a published orbital catalog. When a survey identifies a candidate Trans-Neptunian object, a faint moving dot that repeats across multiple exposures in the expected manner, a decision is made by people with finite resources and finite telescope time about whether to invest the months of follow-up observations necessary to characterize the orbit precisely enough to be useful. That decision is not made randomly. Objects with unusual or extreme orbits, objects that appear to be far out, highly eccentric, steeply inclined, are more likely to receive follow-up than objects whose preliminary orbits look mundane. Extreme objects are more likely to be published. They are more likely to attract computational follow-up, to be run through dynamical models, to appear as test cases in subsequent studies. And in a field where the Planet 9 hypothesis has been the dominant framework for thinking about extreme trans-Neptunian objects since 2016, the objects whose orbits appear to fit the hypothesis are the ones most likely to be recognized as significant and most likely to complete the journey from detection to published orbital solution. The objects that do not fit, the ones pointing in the wrong direction, the ones that should dissolve the clustering signal if included, are less likely to make it through the full pipeline to a useful published orbit. Not because anyone is dishonest. Because human attention is finite, resources are finite, and the objects that look interesting within the prevailing framework receive more of both.
This is not conspiracy. It is the sociology of science operating by the same general principles that govern human attention in any competitive domain. Thomas Kuhn spent a career documenting it. It is not unique to astronomy, but it has a specific implication here. The clustering signal in the published catalog of extreme trans-Neptunian objects may be partly maintained, not by what is actually in the outer solar system, but by what has successfully navigated the entire human pipeline from detection to characterized and published orbit.
The sixth survey argument is Batygin and Brown's strongest card, and needs to be dealt with directly rather than dismissed at the structural level. The argument is genuinely important. The original 6 extreme trans-Neptunian objects showing clustering were discovered by 6 different survey teams working at 6 different telescopes across roughly a decade. If the clustering were a simple artifact of a single survey's directional preference, if one team had repeatedly looked at one region of sky and found things there because they only looked there, the argument for Planet 9 would be transparently circular. You pointed east. You found things in the east. Eastern clustering does not require an eastern planet. But when 6 independent teams, pointing at different parts of the sky at different times with different instruments, all find objects whose orbital long axes align in the same direction, the circularity argument is substantially harder to sustain. The objects came from different pointing histories. Their clustering survived the combination of multiple different search geometries. This is exactly what you would expect if the clustering reflects something real in the underlying population. This argument is sound in principle, and it is not being dismissed. It is why careful astronomers who have no personal stake in the Planet 9 hypothesis have taken the hypothesis seriously, rather than filing it with Brady's retrograde Saturn mass planet. The multi-survey origin of the original sample is genuine and meaningful evidence against the simplest version of the bias objection. The problem is the specific nature of the bias being proposed. The 6 survey argument effectively answers a directional bias, a single survey repeatedly looking in a preferred direction.
It does not answer a structural bias in the same way, because structural bias does not vary between surveys operating from the same planet in the same historical era under the same physical constraints. Here is what a structural bias looks like in practical terms. Every ground-based survey of the outer solar system shares limitations that no amount of independent replication can remove, because they are not properties of individual survey choices but of the physical situation of all astronomical observation conducted from Earth's surface.
The galactic plane, that dense band of stars stretching across the sky that represents the edge on view of the Milky Way, is effectively excluded from essentially all ground-based trans-Neptunian object surveys, regardless of the specific choices of any individual team, because the background star density there is simply too high to identify faint, slowly moving objects against. The atmospheric conditions necessary for finding extremely faint, distant objects, low water vapor, dark skies, calm seeing, occur preferentially at a small number of high-altitude sites whose geographical distribution is uneven. Seasonal constraints that determine which portions of the sky are accessible at opposition change slowly and are shared by all programs operating in the same era. These are not individual survey choices. They are structural features of what it means to search the outer solar system from the ground in the early 21st century. Now consider what this means for the clustering calculation at the geometrical level. The longitudes of perihelion of extreme trans-Neptunian objects describe directions in the solar system, which way the orbital long axis points in space. They do not directly describe positions on the sky as seen from Earth at any given moment. An object's perihelion can point in any direction, and the object can currently be anywhere in its orbit. So a sky coverage bias does not directly map to an orbital orientation bias in an obvious way. This is Batygin and Brown's correct technical objection. You cannot simply wave away orbital clustering by pointing to which parts of the sky surveys searched. But there is a connection between sky coverage and orbital orientation that operates indirectly through the geometry of perihelion detectability, and it is real. Objects in highly eccentric orbits, which all extreme trans-Neptunian objects, are, by definition, are detectable only when they are near perihelion. They spend the vast majority of their orbital period in the cold, distant, faint portions of their orbits, reflecting too little sunlight to be found by any current survey. They become detectable only in the narrow window around perihelion, when they have swung close enough to the Sun to brighten significantly. For an object with a 10,000-year orbit, this window might be only a century or two. The entire known inventory of extreme trans-Neptunian objects was found in this perihelion window, found not where these objects spend most of their existence, but in the one location along their paths where they were bright enough to be noticed. This means that the longitude of perihelion, the orbital parameter that clustered, describes not just an abstract direction in the solar system, but also the approximate direction in space where each object was located when it was found. And the direction in space where an object was located when it was found is related to the direction on the sky where the survey was looking when it found that object. The relationship is geometrically complex. It is not a simple one-to-one mapping, but it is real. The structural limitations of ground-based surveys, which concentrate searches in certain ecliptic longitudes and certain galactic latitude ranges, do filter for certain perihelion orientations preferentially over others, through the indirect route of perihelion detectability geometry. Lawler's simulations demonstrated this computationally.
6 independent surveys, all operating under the shared structural constraints of ground-based optical astronomy, would all be preferentially sensitive to objects whose perihelia pointed in the portions of the sky that ground-based surveys can effectively search. Not identically sensitive, their different pointing strategies and seasonal cadences would weight them differently, but sharing a structural preference that does not vanish when you add more independent surveys, because independence within a shared constraint does not eliminate the constraint.
This does not prove the clustering is entirely an artifact. It establishes that the clustering is expected, at least partially, from the observational conditions alone. And it means the 0.007% probability, calculated against a perfectly uniform expectation, without accounting for these structural factors, is not measuring exactly what it was presented as measuring. Then there is a specific detail about one of the original 6 objects that makes this geometrically concrete. The object 2013 RF98, one of the 6 whose clustering Batygin and Brown cited, was discovered by a predecessor survey to OSSO's using the same Canada-France-Hawaii telescope. When the OSSO's team ran their survey simulator on 2013 RF98's orbital parameters, asking what the probability of detecting an object in that specific orbit would have been given the conditions of the survey that found it, they found that the longitude of perihelion of 2013 RF98 fell in a range of values that was preferentially accessible to that survey's observational geometry. Objects with orbital orientations, placing their perihelia in certain other directions, would have been less likely to be found by the same survey under the same conditions, not because of any systematic pointing preference, but because of how perihelion detectability interacts with the survey's seasonal coverage. One object in a detectability sweet spot is not a bias, but one of the 6 founding objects being in such a sweet spot for the survey that found it is a concrete example of the more abstract argument about structural bias. The prediction has been moving since the day it was made, and the direction it has moved deserves explicit attention. The original 2016 estimate placed Planet 9 at 400 to 800 astronomical units from the Sun, with a mass between 5 and 10 times Earth's. That was the version that entered public consciousness. By 2019, the refined estimate had tightened the mass toward the lower end of that range and settled the most likely semi-major axis around 500 astronomical units. The 2021 Brown and Batygin updated orbital solution incorporating a larger sample of extreme trans-Neptunian objects and more sophisticated dynamical modeling, placed the semi-major axis at 380 astronomical units, with a best-fit mass of about 6 Earth masses. More recent analyses, incorporating additional objects and refined modeling, have estimated the mass at around 4 to 5 Earth masses, toward the smaller end of all previous estimates, and placed the semi-major axis closer to 300 astronomical units than to the original 700. Each of these revisions is presented as science refining itself in the normal way. More data, better models, tighter constraints. That description is accurate. But there is a direction to the refinements that is worth naming separately from the explanation of them. The prediction has moved consistently toward a planet that is smaller and closer than originally proposed. A planet that is smaller reflects less sunlight. A planet that is closer reflects more sunlight. These two effects partially cancel, but the net result of a smaller, closer object compared to a larger, more distant one is a brighter predicted object, more detectable by existing surveys. And the surveys have not detected it. 78% of the sky area where Planet 9 is predicted to orbit has now been searched at a depth sufficient to find a planet of the estimated brightness by the combined efforts of the Dark Energy Survey, the Zwicky Transient Facility, and Pan-STARRS. The remaining 22% includes the galactic plane, where background star density defeats current optical survey capabilities, and a smaller fraction of sky that simply has not yet been covered at sufficient depth. If the planet is distributed uniformly in probability across its predicted orbit, a 78% sky coverage with no detection significantly reduces the prior probability that the object is real. The calculation is complicated by the fact that detection sensitivity varies across the searched region, and the planet's predicted brightness depends on where it currently sits along its elliptical orbit. But the basic direction of the inference is clear. More sky searched. Still nothing found. Battigan and Brown have acknowledged this honestly. They have noted that the planet could currently be near aphelion, at its farthest and faintest, in the portion of sky that includes the galactic plane, a configuration that would render it undetectable even if it exists. This is a legitimate refuge. An object at aphelion near the galactic center could plausibly evade all current surveys. But a hypothesis whose predicted object keeps being most likely to reside in the portion of sky that is hardest to search is a hypothesis that has had the good fortune of never being precisely falsifiable at any given moment. That pattern can reflect a legitimate sequence of genuine constraints, pushing the prediction toward the remaining unsearched region, or it can reflect a hypothesis that is flexible enough to survive any non-detection while unsearched sky remains. Distinguishing between those two interpretations requires completing the sky coverage, which leads directly to what is now happening on a mountain in Chile. The April 2025 infrared candidate needs to be held against all of this, because it is the sharpest recent illustration of the gap between calculation and physical reality. Terry Longfan and colleagues at National Tsinghua University in Taiwan published a paper describing a search, through archival data, from 2 infrared all-sky surveys separated by 23 years, NASA's IRIS satellite from 1983 and Japan's Akari satellite from 2006 to 2007. At the distances where Planet 9 is predicted to orbit, it would move roughly 3 arc-minutes per year, a tiny but measurable drift over 2 decades. After applying positional and flux criteria and inspecting 13 candidate pairs, the team found one object that survived every filter, a source in IRIS that was absent from the same coordinates in Akari, and a source in Akari at a position consistent with slow motion from the original IRIS detection. Mike Brown, when asked about this, responded immediately. "If the object is real," he said, "it is not Planet 9 as predicted. Its implied position and orbital motion are not consistent with his model. His best estimate was that it was noise, but he added that it would be interesting to find out. The man who has spent 9 years predicting this planet looked at the strongest observational candidate yet reported and identified it as inconsistent with his prediction. His own planet, found by someone else, in roughly the right distance range, not in the right place. Then came 2017 OF201. See how Cheng and colleagues at the Institute for Advanced Study in Princeton announced this object in May 2025. It was found using archival images from the Victor M. Blanco telescope and the Canada-France-Hawaii telescope, captured between 2011 and 2018, and identified computationally using an efficient algorithm Cheng had developed. The object's perihelion sits at 44.5 astronomical units, similar to Pluto's distance. Its aphelion extends more than 1,600 astronomical units from the Sun. One complete orbit takes approximately 25,000 years. The object is potentially 700 kilometers across, large enough to qualify as a dwarf planet. And its orbital orientation points roughly 90 degrees away from the direction of the clustering that motivated the Planet 9 hypothesis. When Cheng ran dynamical simulations, the result was specific. If Planet 9 exists on the most recently published orbital solution, it would render 2017 OF201's orbit gravitationally unstable on a timescale of roughly 100 million years. That is about 2% of the solar system's current age. An object cannot spend 25,000 years completing one orbit and remain dynamically stable for less than 2% of the solar system's lifetime unless something unusual happened recently in a cosmological sense. Either Planet 9's orbit differs from the current best model enough to avoid destabilizing 2017 OF201, or the object arrived in its current orbit recently and will be ejected in due course. Or the current model needs to be rebuilt on different foundations. Chad Trujillo, one of the two people who originally noticed the clustering in 2014, was equanimous about this. One object pointing in the wrong direction does not refute a model that predicts a dynamically complex population, he said. He is technically right. But absorbing anomalies is what a theory does when it is sufficiently flexible. A theory flexible enough to absorb every anomaly without constraint is not making a prediction about the physical world. It is making a prediction about what combinations of parameters can be accommodated, which is a different kind of claim with different epistemic standing. There is a pattern in the Planet 9 hypothesis that accumulates across 9 years of evidence. The clustering signal is real in uncorrected samples, and weakened or absent in bias-corrected ones. 3 independent bias-characterized surveys have found no clustering. The prediction has moved toward a smaller, closer, more detectable object that has not been detected in 78% of its predicted sky. The best infrared candidate does not match the model. The most recently discovered extreme Trans-Neptunian object has an orbit incompatible with the most recently proposed trajectory. Each individual accommodation of each new discordant piece of evidence is locally reasonable. The cumulative picture across 9 years is of a hypothesis that has become increasingly defined by where the planet is not rather than by what it should be doing. This is what astronomers call the falsifiability soft spot, a hypothesis flexible enough to adjust its parameters in response to every new constraint without ever producing a result that would unambiguously refute it, is not, in the strict sense, telling you something about the physical world. It is telling you what the parameter space can accommodate. The Planet 9 hypothesis has not yet reached the point where the accommodations have become untenable. The parameter space is genuinely large, and genuine uncertainty about the planet's current orbital position is real and legitimate. But the direction in which the evidence has been moving for 9 years is consistent, and it has been consistently away from confirmation. The Vera Rubin Observatory sits on Cerro Pacn in the Chilean Andes at an elevation of 2,662 meters. Its primary mirror is 8.4 meters across, composed of a primary and tertiary mirror fused into a single reflecting surface. Its camera, the LELST camera, the largest digital astronomical camera ever built, contains more than 3 billion pixels and covers 9.6 square degrees of sky in a single exposure. That is enough to photograph more than 40 full moons simultaneously.
Over its planned 10-year legacy survey of space and time, it will image the entire accessible southern sky repeatedly on a cadence that will build a time domain map of everything that moves or changes against the fixed background of distant galaxies. In early April 2026, from its commissioning observations alone, before the full survey had even formally begun, it submitted the largest single batch of solar system object discoveries in recent memory to the International Astronomical Union's Minor Planet Center.
More than 11,000 new asteroids. Roughly 380 Trans-Neptunian objects found in less than 2 months of preliminary work. Among those Trans-Neptunian objects, 2 provisionally named 2025 LS2 and 2025 MX348 were found to be on extremely large and elongated orbits, reaching approximately 1,000 times the Earth-Sun distance at their most distant points. Mario Urich, Rubin's solar system lead scientist, described the submission as the tip of the iceberg. What used to take years or decades to discover, he said, Rubin will unearth in months. Kevin Napier, the same researcher whose 2021 result cast the most systematic empirical doubt on the Planet 9 clustering, was part of the team that developed the algorithms for detecting distant solar system objects in Rubin data. He described these distant objects as a tantalizing probe of the solar system's outermost reaches, directly relevant to the question of whether an undiscovered 9th large planet may still be out there. The full survey will find Trans-Neptunian objects by the tens of thousands over its 10-year operational lifetime. It will find them in a fully characterized survey footprint, with a well-understood and carefully modeled detection pipeline across the entire accessible sky. It will produce a bias-corrected map of the outer solar system's orbital population that is orders of magnitude more complete than anything currently available. And it will, in the process, produce the definitive answer to the question the Planet 9 debate has been orbiting for 9 years. Is the clustering real when you can actually see what you were previously unable to see? If the clustering survives in the complete Rubin sample, if, after correcting for all the biases the survey can characterize, the extreme Trans-Neptunian objects still concentrate their long axes in the same direction, in numbers large enough to eliminate the small sample objection, then the Planet 9 hypothesis will stand in a substantially stronger position than it currently occupies. The signal will have persisted through the most demanding test it has ever faced. If the clustering dissolves, if the bias-corrected Rubin sample, with its thousands of outer solar system objects mapped across a full and characterized sky, shows a distribution that is uniform or close to uniform, then the hypothesis loses its primary observational foundation. The planet could still exist. An object at several hundred astronomical units is too far for Rubin to detect directly with high confidence, even with 8 meters of mirror. But an absence of clustering in a complete sample would remove the reason to believe the planet is there in the first place. It would return the question to the anomalous individual objects, Sedna, 2012 VP113, 2017 OF201, and to the multiple separate explanations for those objects that Planet 9 had temporarily unified. Either outcome will be informative in a precise and meaningful way. The era of arguing about whether the sample is representative enough to support the calculation is coming to an end. Here is what the long examination of this question has found, stated as plainly as it can be. The outer solar system is genuinely anomalous. That is not in dispute, and it is the foundation on which everything else in this discussion rests. Sedna is where it should not be. and that statement is not dramatization. Its perihelion at 76 astronomical units is too far from the Sun to be explained by Neptune's gravity in any current model. 2012 VP113 is in a similar situation. 2017 OF201 reaches 1600 astronomical units at aphelion and takes 25,000 years to complete one orbit, and its existence in a stable path at that distance is, on its face, as difficult to account for as Sedna's. The outer solar system is populated by objects in orbits that the forces and objects we know about cannot easily produce. This is not a hypothesis. It is an inventory of things that are actually there. The question is, what made them that way? Planet 9 is one answer. A planet 4 to 5 times Earth's mass, orbiting somewhere around 300 to 700 astronomical units from the Sun, on a highly eccentric path, tilted relative to the plane of the other planets, gravitationally herding the extreme objects into aligned orientations through slow and patient influence over hundreds of millions of years. The mechanism is well understood. The dynamical simulations are sophisticated and internally consistent. The predicted object would account for multiple independent anomalies simultaneously. If it exists, it is the largest undiscovered object in the solar system, a world present throughout all of human history, moving through the same sky we have mapped and catalogued across centuries, never once leaving a trace that any instrument ever detected. Passing stars are another answer. In the first billion years of the solar system's existence, when the Sun still orbited within the stellar cluster that formed alongside it, neighboring stars passed close enough to the outer solar system to scatter objects onto detached orbits that survived the cluster's eventual dispersal. Those stars are now distributed across the galaxy.
But the objects they scattered remain behind, carrying the gravitational fingerprint of encounters that lasted perhaps 1,000 years and happened 4 billion years ago. Sedna may be one such object. Neptune's migration is a third answer. The NICE model proposes that the giant planets formed in a more compact configuration and migrated outward over the solar system's early evolution, with Neptune moving substantially from its original position, crossing resonances and scattering smaller bodies across the outer solar system as it went.
The frozen record of that ancient migration may be what we are reading in the orbits of the extreme objects. A fourth possibility, proposed by Jakob Schultz and James Unwin in 2019, is that there is no undiscovered planet at all, but rather a primordial black hole, an object of roughly 5 Earth masses formed in the extreme conditions of the early universe, captured by the solar system during a close encounter during the Sun's time in its birth cluster, now orbiting silently at several hundred astronomical units, emitting no light. Such an object would be approximately the size of a grapefruit. It would be effectively invisible to any optical or infrared survey. Its gravitational influence on the outer solar system would be indistinguishable from a planet of the same mass. Only the absence of any infrared thermal emission distinguishes it from a planet, and the fan candidate, which was a thermal detection, seems to make this option less likely, assuming that candidate is ever confirmed. Since Brown himself believes it is probably noise, the primordial black hole option remains technically open. These answers are not equally well supported. Planet 9 and Neptune migration have the most developed theoretical frameworks and the most active research communities. The passing star hypothesis is broadly accepted as a real mechanism for some objects, but disputed as a complete explanation. The primordial black hole proposal is speculative, but not physically excluded. What all four share is that they cannot currently be distinguished from one another by the available data. The orbital clustering is present in some samples and absent in others. The anomalous objects are real, but explicable by multiple mechanisms. The planet has not been found. Then there is the possibility that the real explanation requires a framework that does not yet exist. This deserves naming rather than setting aside, because the history running through this entire account contains one clear case where that was the answer. Leverrier's anomaly in Mercury's orbit was not explained by a better search for Vulcan. It was explained by a man working on an entirely different problem, the reconciliation of special relativity with Newtonian mechanics, who found that the framework everyone had been using to calculate planetary orbits was not quite right, and that when the correct framework was applied, the anomaly dissolved without any additional planet. Einstein was not looking for Vulcan's replacement. The solution to Leverrier's problem fell out of his work as a consequence of solving a deeper one. The outer solar system anomalies may be explained by a planet, which would require no revolution in anything at all. But the shape of the situation is similar enough to the Vulcan case that the possibility of a deeper explanation deserves at least the acknowledgement that it exists, rather than being treated as too exotic to mention. There is a quality to honest not knowing that is different from ordinary ignorance. Ignorance is the absence of information. The not knowing that matters here is the presence of information that has been examined carefully and found to be insufficient. The condition of having pressed on something with the best available tools, from multiple angles, and arrived at the place where the tools run out before the question resolves. That is where this stands. The phrase mathematically certain describes not a property of the solar system, but a property of a calculation performed on a sample whose representativeness is in genuine dispute, producing a probability figure that is conditional on assumptions that have not all survived scrutiny, expressing a confidence that properly belongs to the arithmetic and not to the inference drawn from it. The certainty is in the numbers. The numbers are about the sample. The sample is not the solar system. Leverrier found Neptune and the triumph was real, and it was also luckier in its details than the story told about it. Lowell predicted a planet, and a young man from Kansas found something in roughly the right region of sky for reasons that had nothing to do with the correctness of the prediction. Vulcan was predicted with the same method, the same confidence, the same mathematical precision, and it did not exist. And what turned out to explain the real anomaly it was supposed to explain required dismantling the most successful physical theory in the history of science and rebuilding it from different foundations. The outer solar system is doing something. The models say a planet is the most economical explanation for what it is doing. 9 years of active searching across 78% of the predicted sky have not found one. The evidence for the clustering that motivates the prediction weakens every time the observational correction is carefully applied and does not completely disappear. An object at several hundred astronomical units, if it exists, has been moving through the sky above every human civilization that ever looked up, present the whole time, exerting a gravitational pull so slow in its accumulated effects that only decades of careful orbital data reveal even its shadow. It may be there. The absence of a detection is not a detection of absence. The Vera Rubin Observatory, which found 380 Trans-Neptunian objects in less than 2 months of its first early observations, will spend the next decade answering the question that 9 years of argument have not been able to settle. If it finds the clustering undeniable in a complete, bias-characterized, all-sky sample, then Planet 9 will be the most probable explanation for something real, and the direct search will have a foundation strong enough to justify whatever it costs. If the clustering dissolves in the complete picture, the anomalies of the outer solar system will scatter back into the multiple separate explanations that Planet 9 temporarily unified into one, and the searchers will have found that the sky in that direction contains what most of the sky contains: cold and dark, and objects whose names we do not yet know. Corey Shankman spent 4 years mapping what a telescope could and could not see from the summit of a mountain in Hawaii. He built the most careful account of observational bias the field had yet produced. He found 840 objects and 4 years of data and a fully characterized model of what he could not find. He found no clustering. He said the survey found no evidence requiring a planet. And he did not say there was no planet. The solar system, he said, is an exciting, weird, and often mysterious place. It may well turn out that there is another planet out there. But in our survey, we find no evidence requiring one. That is the precise location of the uncertainty, not the absence of a planet, not the confirmation of one. The place where the evidence, examined as carefully as it can currently be examined, runs out before it reaches the object. The math is real. The inference from the math to a physical thing is the step where everything that cannot be calculated has to be carried by the quality of the observations, the honesty of the bias correction, and the willingness to let the evidence be what it is, rather than what the calculation was hoping to find. The outer solar system is doing something. Whether that something has a name yet, whether it is a planet moving in darkness at the edge of everything we can reach, or a gap in our understanding of how solar systems are assembled, or simply the accumulated shape of our own blind spots turned outward against 4.5 billion years of history that we are only now learning to read, is not a question the mathematics resolves. The mathematics is the question. The outer solar system is the answer we have not yet been able to hear.